85% of the general public believes that within 25 years that the dominant source of our electricity is going to be from the sun. And our Energy Information Agency, which says that with 90% probability, the dominant source of our electricity within 25 years will still be coal and will be there for the next 50 years. That's our business as usual. And the question is, how would we get off that? Of course, we have security of supply issues. We have security of supply issues with respect to gasoline in particular. It comes from parts of the world that don't always like us. And the price can go up or down, but when one looks at the fossil resource base, one finds that we, like it or not, have a lot of coal. We are the Saudi Arabia of coal, in fact. China is a close second to that. And in fact, we could be energy independent if we wanted to by just utilizing coal for both our electricity needs and for a large part of our liquid hydrocarbon transportation needs. We know this can be done. Germany did it on a dime in World War II. They flipped their whole economy when denied oil by the Allies to run on coal. South Africa, when denied oil from apartheid, turned their coal into liquid hydrocarbon fuels at $40 a barrel. They do that today in what's called the Fischer-Tropsch process to make clean diesel fuel that they run their vehicles off of. We could do that again here in the United States if we wanted to pay for energy security. And the good news is we have hundreds of years worth of supply of coal where the demand is in the United States, in China, and in many of the other developed countries. The bad news is that if we have to be careful what we wish for, we might get it. Here's what the carbon dioxide levels have been on our planet on the 400,000 year time scale. I'm sure many of you have seen this plot. They've been in a range of between 200 and 300 parts per million as described by looking at the bubbles in ice cores in the Antarctic and Arctic regions. And we know that changes of 100 parts per million have not once, but 1, 2, 3, 4 times repeatedly been correlated with, but are not completely proven to be the causes of, temperature changes that have led us into ice ages. On this same record, over 400,000 years, now extended to 670,000 years, when the CO2 concentrations in our atmosphere have never been above 310 or 320, this is what it looks like in the last 50 years. We know this comes from anthropogenic fossil fuel burning. The carbon has been dated and isotopically labeled. In addition, CO2 coming from the oceans into the air releases CO2. But when you burn a candle, you consume O2. And in fact, we've actually measured the decrease in oxygen by a little bit in our atmosphere that exactly balances the amount of carbon that's being burned by humans. So there is no technical doubt that this rise in CO2 is not due to some fluke of the oceans, but is completely due to humans burning fossil fuels. Of course, this is obvious to anybody but the most ardent skeptic, because when you fill up your gas tank and after you go for a tank full, it's empty, and where do you think it went? Well, it went into the air, all right? So there's no doubt about this. The further important point here is that at the rate we are going, you hear we will stop emissions. We don't intend to stop emissions. We intend to stop potentially the rate of emissions increase. That's a very different thing. The reason is that the lifetime of carbon dioxide in our atmosphere is about, a good number is 3,000 years. That's for the half of it that's emitted that isn't equilibrated with the near surface oceans and the plants. What happens to the rest of it? It's not like ozone that heals itself naturally because there's a reaction to make and destroy it. There's no natural destruction mechanism of carbon dioxide. And that means that what we do on the next 50 years within our lifetime is going absolutely on the course we are on to change the atmosphere of our planet for a timescale comparable to modern human history. You can argue all you want about whether or not this will be good, maybe, and there will be winners or losers, about whether or not climate models are right or wrong. that is absolutely, at some level, irrelevant. This is not about waiting to predict the climate in the year 2050 with scientific certainty, because I will make the only scientifically certain prediction about when we can do that. And that is when we open up our door on New Year's Day, January 1st, 2050, and look at the Bears in the Rose Bowl playing the game and look at the weather. This is not about sound. You can decide which you think is more of a probability of happening there. Nevertheless, as an old Stanford professor, I must add, by the way, I have some bias in this regard. Nevertheless, this is not about sound science. This is all about risk management, pure and simple. CO2, our best knowledge says, lasts for thousands of years. And we will be putting up enough in the next 50, knowing that changes of this level have been correlated with temperature changes that have got us into ice ages that are going to bring us off of this chart. Furthermore, even if you stopped increasing the rate of emissions, that just stops increasing the rate of its growth. That doesn't mean it would stop still accumulating. That just means you're not accumulating it more and more rapidly. What is there will simply, by that time, not go away. That is the problem. In fact, good estimates say that if you wanted to stop the rate of its buildup at double the level that humans would otherwise have ever breathed, a level that nobody can tell you is or is not safe, you would have to cut current emissions levels by about 80% of the present. Stopping the rate of buildup just stops the increasing rate of you accumulating debt, but it doesn't let you pay off your credit card. And we need to find a way, if we don't want to take this risk, of paying off our mortgage. You've seen pictures like this, where we see 10 years worth of Greenland ice melt. We know that if Greenland continues to melt, unequivocally there's enough ice there that sea level will rise 20 feet. Do we absolutely know that human-induced warming is causing this? By the definition of absolute proof in science, the answer is no. Because we teach our kids in 3rd grade what a scientific hypothesis is. You remove the thing that you think causes the effect and you run the experiment again, and if the effect goes away, then you have proof. Well, last time I looked, we can't rewind the Earth for 100 years and develop the industrial age again without carbon and see what our planet would be like in another 50 years to prove that CO2 is the cause or not of this. All we can say is what we see now. We ought to understand the rate of ice melting, and in fact, a survey of glaciologists 6 years ago said that we thought in best estimates that in 50 years there would still be ice in the Arctic with about 80% of the ice that was there currently. But in fact, the ice is melting much more rapidly than the most rapid models predicted because we didn't understand crevassing and forming of moulins and lubrication of the ice sheets. The Antarctic was supposed to maintain, in fact, increase its ice volume because it would have to warm up by 4 or 5 degrees to melt the Antarctic, and due to the extra humidity elsewhere on our planet, that would lead to an increase in precipitation and more snowfall in the Antarctic, increasing its volume. That happened for a little while until the ice sheets melted at a rate far beyond what the models predicted. And now the Antarctic is melting, and now a survey, best knowledge of glaciologists, says that within 15 years it's very likely there won't be any Arctic ice left in many places, maybe at all. CO2 is also an acid. Even if you stopped its radiative transfer, anybody that's drunk a soda knows that CO2 when added to water makes it acidic. The pH of the near-surface oceans is now lower than it has been in several million years, and soon will be lower than it has been in 20 million years. 20% of the coral on our planet is now bleached. Many, but not all, climate models predict that all of it will be bleached within our lifetimes. And if you have a 16-year-old like me, you tell him he has two choices. He can either go see that coral now, or I'll give him a copy of that old movie, Finding Nemo, to remember what it looked like. There are also issues with respect to the permafrost. That is, the climate models are linear models. They linearly extrapolate the present to what the future might be, but we're not very good at extrapolating to a future that humans have never been in before. Nobody has lived in a doubled CO2 atmosphere. We know there are effects like this permafrost, which used to all be ice. It's now melted. The helium bubbles trapped in this permafrost tell us it's melted in places it hasn't melted in at least 40,000 years. And when this ice melts, it used to reflect sunlight because, as anybody knows that's been on a white surface, that is very reflective and bright. As this melts, it gets warmer and absorbs more sunlight. That releases more otherwise not melted permafrost that accelerates catalytically this runaway train effect. We know that CO2 levels due to this permafrost and methane levels, it contains enough that the levels won't rise by a factor of 2, but they could rise by a factor of 5 to 10. Now, we know this did happen once before on our planet when there was a massive isotopically release of carbon dioxide. We know that temperatures spiked 6 degrees. We know that it lasted for tens of thousands of years, if not longer. We also know from the fossil record that 90% of the species then on Earth went extinct. We absolutely do not know that would happen again. We absolutely do know that there is only one way to find out. And so that is the decision that we are making as a society, and we, in fact, are uniquely positioned as the generation which gets to choose which path we will take. We get to choose a path that will either bring generations to come a fundamentally different planet than the one we have now, or we get to take credit for the solution of not going there. And that's the choice we really are making. Well, I told you that current energy load is 14 trillion watts, and I also told you that we had to cut emissions by 80 or 90% relative to where they are now. The challenge is, however, greater than that because we don't live in a static world. We live in a world where many, many more people, like the 2 billion people in India that live under $2 a day, that don't use much energy yet, and the Chinese and many others want to be like us. They want to be Americans. They want to have the energy efficiency and energy consumption commensurate with getting out of poverty. And in fact, most analyses say that if we're lucky, we can hold energy demand to double within 50 years. In fact, if we conserve as much energy as all the energy we use today combined, we might hold it to double, and maybe if we do better than that, we might hold it constant. Well, if we held energy demand constant but kept getting it all from fossil energy, then we would still be adding carbon dioxide to the atmosphere, and instead of doubling in 2050, we double in 2060. It doesn't help you very much. You simply have to find a way to not only save as much energy as all the energy we use today combined, but that'll avoid you doubling to keep it constant. If you want to cut emissions, you also have to make as much energy as all the oil, coal, gas, and nuclear power that we use today combined. Put simply, that is the energy challenge. To give you a feeling for how much and how big that challenge is, if you save energy down to twice the level it takes to eat, on average over our planet, including the energy it takes to grow the food and deliver it, then you only have to make as much energy as all the energy we use to hold CO2 to double where it is today. Now, it's not clear that's a solution if you're happy with bringing the world to a place it's never done before, but that's the scale of what faces us as a society. If you want to get that 14 trillion watts of what you make now, both saved and then equivalently generated from carbon-free power, if you want to solve this problem, there's only one technically credible, proven way at scale to do that now. That way is, like it or not, nuclear power, nuclear fission. You have to be careful what you wish for. We build nuclear fission reactors at about 1 gigawatt, and that's the level at which we can permit them to be safe and hold that heat and radiation flux within that concrete confinement chamber. If you want to get from here to there with nuclear power, to get to 14 trillion watts, each one providing 1 billion watts, you only have to build 14,000 nuclear power plants. That also happens to be 1 reactor a day, every single day for the next 38 straight years. That is the scale of our energy challenge. If we build 1 a week, we leave 95% of this problem on the table. Our nation's #1 energy policy is clean coal. From the point of view of carbon dioxide emissions reductions, clean coal is an oxymoron. By cleaning up only the mercury or sulfur, you have to bury the carbon dioxide somewhere. We could think about putting it in the oil wells where natural gas has stayed for geologic times. But in fact, there's only 30 years worth of global capacity. And don't be fooled when oil companies tell you they're putting CO2 down in reservoirs to hold it, because what they are doing is pushing back up more oil than the CO2 they're pushing down. So they're actually making more net carbon than the carbon that they're storing. The only place to really put it is on underground aquifers. And we don't yet know technically whether or not that will work at scale. And by scale, I mean billions of tons a year, every year, not leaking for the lifetime of carbon dioxide in the air for 1,000 years. After all, if 1% of it leaks and you're doing it for 100 years, the net flux is the same at the end of what you started to avoid in the first place. So we should absolutely be doing technical measurements to understand whether or not we can actually bury billions of tons of CO2 below our soils and feel comfortable with the risk that that might entail technically. By the way, no company wants to assume that risk. They all want, if forced to bury it, and then after 10 years of burial to leave the government to have the liability in case something goes wrong, because no company wants the liability on their books for more than a decade. So we have an interesting policy decision to think about there. And then there are carbon-free sources, because if you only, say, take coal and sequester enough for a few billion watts, and you get a trillion watts rather, you get a few trillion watts out of nuclear, you still need 10 or 14 trillion watts from something else. That's assuming you save as much energy as all the energy we use today. So where can you get that? Well, you can't get it from the wind. There's only 2 trillion watts or 3 to be had technically. Wind is a great thing to do. It's the fastest growing renewable resource, but it's going to be up against the stop sooner rather than later if we actually tried to use it exhaustively. The same holds for ocean and tide currents. We have some in the San Francisco Bay, and there's a lot in the Bay of Fundy, but when you all add it up, there might be 2 terawatts on all the waves, tides on our planet combined. If you took the heat of the Earth and took all the land on all the continent, combined it, and had 100% efficient heat engines covering every square foot of all the land on Earth, you might get 12 terawatts. So this shows you the heat of the Earth isn't close to satisfying our thirst for energy as humans on our planet. Sure, we could cut back tremendously, and then we end up not using much energy and not consuming much energy and living like humans lived in the 1800s or like people live when they have 1 candle to burn at night. And it seems like that's not really a desirable option. Hydroelectricity's maxed out. We know that. 0.9 terawatts is what's economically feasible. We produce 0.6 already. You heard from Chris Somerville about biofuels. You should understand that biofuels are, in principle, a good way to offset some amount of liquid transportation fuel. And that's a very good use for nature's gold, which is carbon-carbon bonds in the form of sugars. But when you look at a plant, first of all, it's the wrong color. It's green. It should be black. If you wanted to really be a machine to absorb sunlight, all solar cells are black because we designed them, because we can match them to the spectrum of the sun. The second point is that it's not well appreciated that plants stop producing fuel at 1/10 of the bright intensity of a bright sunny day. They shut down. And the reason they shut down is because the enzymes used, this enzyme called rubisco, that actually is involved in fixing carbon dioxide, can't take the electrons from the light absorption of the sun in a plant fast enough. And so they would build up to very high levels and make oxidative damage. Plants already spend a lot of their energy rebuilding the machinery of that plant every 30 minutes. And if they turned on to the full light intensities of the sun, they would have to rebuild themselves every minute or less. And you would take a tremendous amount of energy to do that. So the fact that plants saturate at 1/10 of a sun and the fact that they're the wrong band gap combined means that their upper limit is going to be about 1% of taking sunlight and storing it. And that means that, like it or not, we're going to have to practice agriculture on the scale of agriculture. We can choose to some extent food or fuel or have them both. But if you take very fast-growing plants, and if you planted them everywhere we currently don't use to feed ourselves, and no energy in and no energy out, you might get 5 terawatts. So they could be a partial step to liquid fuels, but you can't look to them entirely to close this gap. I just want to inject one more point here, just so you understand, that last year in the United States, 25% of our corn was used to offset 2% of our transportation fuel. And we have a law that went through Congress, the Energy Act of 2007, that says within 10 years we have to do 5 times as much as that. Quick math says that 5 times 25% is more than all the corn we currently grow to offset 10% of our transportation fuel. So that gives you a feeling of the difference between the laws of physics and the laws of politics, and only the latter can be repealed. There's one big number. The big number is the sun. The reason plants can be a contributor to this energy problem is because they use, although very inefficiently, the biggest resource that we have, and that's the sun, which doesn't give us tens of terawatts, it gives us 120,000 terawatts. The way to think about that is more energy from the sun hits the Earth in 1 hour than all the energy we consume on our planet in a year. That's the ratio. Oh, it also turns out that we spend more money buying gas at the pump in 1 hour than we fund all solar energy research in our country in that same entire year. No other energy source can make both of those statements at the same time. Willie Sutton's my favorite person to quote here. Willie Sutton was the bank robber, and they finally caught him and they asked him, "Why do you rob banks, Mr. Sutton?" And he said, "Because that's where the money is." Well, if Willie Sutton were involved as a CEO of Energy Engineering Incorporated, he would say, we need to go to the sun because pure and simple, that's where the energy is. We have 3 ways to do that. We have nature's machinery. It makes plants, makes fuel, not a fuel we can use, and so there are challenges that people like Jay Kiesling and others are embracing in trying to convert the lignocellulosic and particularly the cellulosic material into a fuel that we can use. And that's an important thing to do to offset part of our liquid transportation fuels. But at the same time, we need to get tens of terawatts. A good way I tell people on the street to think about your footprint is try mowing your lawn every day and taking all the stuff you get, and how far do you think you would be able to go if you put that all into your car? So that gives you a feeling of your carbon footprint on the scale of agriculture. You can offset a little fuel that way, and it's helpful, but meeting all energy needs will be tough. We know solar cells make electricity. Instead of with 0.2%, 0.3%, they can be 20% efficient. There are only 2 problems. One, they're way too expensive right now, so lowering the cost of solar electricity is an important goal. California, of course, in our state, one of the leaders in the United States, we have signed by the governor, who I'm supposed to see back in Southern California at a meeting tomorrow, in fact, the goal of having 1 million solar roofs in 10 years. That's an important step. But let's not be fooled by the scale of the numbers. I already told you we need 14 or 15 trillion watts. In the United States, we need about 5 trillion watts. The average solar roof is about 2 kilowatts peak, but averaged over the day-night, that's about 400 watts average. That means we would only have to build 1 million roofs a day, not in 10 years, a day, every day for the next 50 straight years. That's the scale of the energy challenge. Oh, and if we did all that and had 1 million solar roofs a day every day in our country, we would have another problem. And now I'll quote my other favorite pop culture icon here, Johnny Cochran. He that cannot store shall not have power after 4, right? You can't build an energy system around an intermittent resource and expect to get anything but peak shaving for someone else's baseload power. And if we can't find a way to store massive quantities of electricity, of which there is no known cost-effective technical solution, then we don't have anything in a real energy system. Sure, we can pump water uphill. That's good to buffer the summer-winter cycles, but you'd need hundreds of Lake Meads filled every day and emptied every night, because the sun has this nasty habit that, last time I looked, moves around the earth, moves around the sun every night. It goes out regularly, and humans need energy all the time. So we have to find a way to store it. And the most energy-dense way to store energy, other than in a nuclear power system, in the nucleus, is in a chemical bond. And that compels you to think about ways to make chemical fuels from the sun. Because after all, nature figured that out. Why can't we? Why can't we figure out how to do what a leaf did, but better than a leaf, so we don't have to use as much area as nature had to use, which is part of the problem in using a low-efficiency technology. So we work on materials that don't use natural pigments like the leaf does, but use the materials of which solar cells are made. But we want to make the right product, which in the long run is chemical fuel, not the wrong product, which is electricity, which is all we know how to do now. So what we are doing as part of this big effort is trying to directly make fuel from the sun with no wires, because that's the way that we believe can be scaled to both capture, convert, and store the energy from the sun. And if you don't do all three, capture, convert, and store, you don't have much. So that's the missing technical gap. We know this works. Oh, I'm not near my mouse, so I don't know if I can do this and show you this movie. This is a rock. This is a mineral called strontium titanate. And if I were down there, I would be able to click on this. Maybe you want to do it. I think you got it. It's a movie, so if you move the little button over to the center anywhere there, you'll get a little pointer. Yeah, good. Now click on it. There you go. And those bubbles you see are hydrogen and oxygen fuel coming directly from sunlight. There are no wires. This is just like what a leaf would do. It's making a fuel from the sun across a membrane. This will go on for years. And in fact, of the light that this absorbs, instead of 0.2% converted into fuel, 20% of it is converted into fuel. So the good news is that we know this can be done. We know that there are artificial systems that can directly take sunlight and make chemical fuel. It's also true that we would really not rather have the hydrogen. We'd really rather fix the carbon dioxide into a liquid fuel. But it's not the key chemical problem, because the key chemical problem is really to make any reduced fuel. If we can make hydrogen, there are already world-class catalysts that are used at refinery scales to take hydrogen and carbon dioxide and make methanol, to take methanol and dehydrate it and to make dimethyl ether, which is a near ideal diesel fuel. It's a clean cooking fuel. We know how to make liquid chemical fuels from a variety of energy-rich molecules, if only we can make those energy-rich molecules efficiently. So why don't we just have strontium titanate on everybody's roof? Well, you might have noticed one little thing about this. It's white. And that means it's really not absorbing much of the rays of the sunlight, which we all know are in the red, blue, and green. This works great when you hit it with blue or near ultraviolet light, but unfortunately it doesn't work very well when we hit it with the light that most of the sun gives us on Earth. So this would work better if we decided to colonize the moon. And in fact, what happens is that as we change the properties of the material to make it more and more colored, and therefore to have the potential to work better and better in the sun, we find that although they get very efficient, they don't last. They rust, or they corrode, or they degrade. And all the materials that last for years don't absorb much sunlight. And all the materials that absorb a lot of sunlight don't last. And that's what we get paid to do in the lab, is to figure out how nature's teased us into thinking that we know we can, in principle, get from there to here. We just don't know how to do it yet. One way is to just try everything. We're not beyond doing that. We're not beyond thinking we're really smart, because in fact we don't have a really good theory yet of what controls the absorption and stability of all these materials. So what we've done in collaboration now with a scientist, Bruce Parkinson at Colorado State, who has a little different angle, is we've modified a very expensive apparatus, a $100 Epsom inkjet printer. And we squirt out from that ink, not Epsom ink, but we squirt out metal salts onto a glass slide in different combinations by controlling the printer software to squirt from valve 1 and valve 2, just like we'd print the letter O from different colors. And each color is in fact calling us a different metal salt that then we heat up, pyrolyze it to make metal oxides. And it's very easy to screen whether or not these are stable. We take a slide where each little square out of the 256 that we choose to print in a given material, we go out in the sun for a day and we only look at what's left behind. And if we've succeeded and something's left behind, we see if it's colored. And if it's colored, we see which ones are more colored. The nice thing about doing this is there are trillions of possible combinations to explore, but we can have a lot of help. Because in fact, this is so easy, you can do this with a Lego Mindstorms kit now. And so we can have high school and junior high school kids discovering new metal oxides and then going out in the sun and leaving them for a while and then reporting back to us into a database which ones start to work. So one of the hopes is that not only will we get kids involved with physical science and understanding about solar energy, but for all we know, they'll make the discovery that is the lead into the next generation of these materials. If you want more information on how we do that, I'd be happy to provide that later, because we want to get more people involved with this. Now that's a little Edisonian, but we're not shamed. We might discover something interesting that way, and we're just starting on that long excursion. But in the second part of this, I want to remind you that we have a godfather here, which many of you may not recognize from that distinguished picture, but this person is the very well-known and distinguished scientist Melvin Calvin of the Calvin cycle and photosynthesis, and of course of Berkeley and the LBL laboratory. And that's what he looked like later on. When I went to my first Department of Energy Science meeting as a young scientist, he was still an esteemed, being alive, part of that program that I looked up to. And that was in 1982. And he said then to everybody, including me as a young scientist, that what we needed to do was to build an actual artificial photosynthetic system so that we can learn what works and what doesn't, and thereby set the stage of making it better. Well, it only took us about 25 years to heed his advice. And so in 2006 or 2007, we started to actually do that. And I'll give you now an update on what we're doing in that part of this puzzle. And so our goal is to demonstrate that we can put together pieces that would comprise the key components of this artificial mechanical version of a leaf. Nature's done it, but it doesn't do it very well. We want to do it better. You know, birds fly, but they use feathers. Airplanes fly a lot faster, and they use metal. Knowing something can be done is a good clue that we as humans can find out a way to do it faster, better, and cheaper. And it's that clue that we want to build on that nature's given us. So our goal is to take a membrane and to generate fuel from the sun in a cheap, scalable way. We know we need 3 steps. We have to capture the sunlight, and for that we need something that will be dark and absorb that sunlight. We, in my laboratory, like to use semiconducting materials, little kernels of the stuff that is used in solar cells. But we don't want to make a solar cell because that's a single crystal of material that has to go on your roof, and we have to make 1 million a day every day. And I assert, in fact, that unless we can find a way to get it so that you can paint it on for a bucket at Home Depot, or you can roll it out like carpet, we can't get to 1 million a day every day. And so we're only thinking about systems that will let us do that. But integrated in that system, you shouldn't be thinking solar cells, you should be thinking bubble wrap. And in's going to come water like a swimming pool heater, and out's going to come fuel out the other side from the sun when it hits that bubble wrap. My part of this project, as part of this team, is the bubble wrap part that's going to absorb the sunlight and try to get those excited states to be able to make the fuel. The actual catalyst needed to convert those electrons into a fuel to split water are things that we're farming out to the real hardcore people on our team, the people at Berkeley and the people at MIT who are working as chemists on these catalysts. We know nature knows how to do this. In fact, this reaction of taking water and evolving oxygen is what's in green plants' photosystem too. We know the structure of that now has 4 manganese atoms at its catalytic site. We as chemists just don't know how to do that outside of a plant. We know how to make hydrogen from water in the sense that bacteria have shown us the way. There are enzymes called hydrogenases that nature developed to do that very thing. We know we can do that in fuel cells in backwards with platinum. But there's not enough platinum in the world. And we can talk all we want about the hydrogen economy with fuel cells. But when the amount of platinum to power a school bus costs $500,000, as it does now, then pure and simple, as long as that exists, the hydrogen economy is going to consist of stolen school buses, right? We need to find a way to dramatically lower the cost of the key elements, and only through chemistry are we going to make new matter that's going to replace that existing expensive material with a cheap material. Nature tells us how, because it used iron, not platinum. We know fuel cells are poisoned by carbon monoxide and sulfur. We have to get rid of them and pay a price. But nature built carbon monoxide and sulfur into the catalytic molecule site. It uses that for its function. We now know the structure of those things, and chemists are pulling those enzymes out of their reactive sites and building models to try to put them into our systems. So now I'll tell you what our part of this system is going to be like. We know we could do this with an expensive semiconductor. We could take very expensive materials, as has been demonstrated by the National Renewable Energy Laboratory, and split water with expensive catalysts. These form the elements of multi-junction concentrator cells. You don't have to know much more about that except that it costs $10,000 to make a square centimeter of this material. So we need to find another way. The lesson nature tells us is this is how a photosynthetic bacteria works. There's 2 pigments. One absorbs 1 photon of light, but it doesn't demand that it all does the chemical reactions. And it boosts that with the 2nd photon of light. This is one photosystem, that's the 2nd photosystem. We know that from high school chemistry, which many of you probably remember, you had to take a battery and turn it up to 1.23 volts in order to get hydrogen and oxygen coming out of water. You also need 1.2 volts to make methanol from water or to make sugar from water also. It's about the same. So we need 1.23 volts, but we don't want to get it from one material, we want 2, each one of us giving us about 0.7 volts, so we get about 1.4, so we have a little bit to spare. We also know that nature teaches us another important lesson. It makes oxygen at a physically different spot from where it makes the reduced hydrogen. Nature's hydrogen is used in situ to make NADP and NADPH, and then to drive ATP and to fix CO2. The important point is that it physically separates its hydrogen from its oxygen across a membrane. And you don't really have to know much more except the Hindenburg to know why you want to physically separate hydrogen and oxygen across a membrane. So we have to do that too. So if we got to have a membrane, and if we know we want to physically separate materials, that leads us into the key design point. We need to bridge that membrane with something really cheap. And here's the last nature lesson. The last nature lesson is that our concept here is the way to make this really cheap is to change the ground rules of solar cells. Solar cells' ground rules are you take a material and it needs to be a certain thickness to absorb all the light. Less material, just let sunlight go through. That's a waste. Too much material is also a waste. You wasted material. In the case of silicon solar cells, this has to be about 300 microns. So you build a cell 300 microns thick. But that constrains how pure the silicon has to be, because if the light is absorbed 300 microns in, and you demand that the electrons have to make it all the way back to get to the wire to make electricity, that silicon has to be very pure. Otherwise, along the way, it'll hit a trap and make heat, and you won't make electricity. And so you have to pay a very high price in order to purify that silicon to get it to make those carriers move for the depth needed to absorb the light. This is the same reason why organic solar cells don't work well. Although they're cheaper and they're thinner, they don't collect very many carriers either. And all solar cells lie on a common cost per watt curve because of this fundamental physics basis. Well, if you don't like the rules, you should just change the playing field. And the way you can think about changing the playing field is not live with those rules. What happens instead if we were to make a very tall material long enough to absorb the light, but not decide that we have to make it move upwards back the same distance to go to the wire? What happens if we can move it at a right angle sideways? Now it can only move a very short distance because this wire can be very tall but very thin. And in this way, we could use a very cheap material because, in fact, it could be long enough to absorb all the sunlight. And if it's very cheap, the carriers won't move very far, but we just make it thin enough to get them all at the sides. This orthogonalization, this separation by angle of light absorption and collection of electricity is what the design is that we are exploiting as the bridging components of our membranes that we believe will let us get off of this cost per watt curve that all traditional solar absorption materials are on. We know that we could use this to make electricity from the sun, but we want to go to put the puck in the net and really use it to make fuel, because if we don't store, we don't have much. We have a theory that says this will work, but we have better than a theory that says it will work. We have real experience. This is a forest of aspen trees that do exactly that, right? They're growing tall toward the sun to absorb the light, and the nutrients that are heavy don't have to move very far as they move sideways. This is what roots do. This is what leaves do. This is what stomata do. This is what retinal rods do. So if nature figured this out a long time ago, that's a pretty good clue that what we just figured out with equations recently probably is something worth exploring. So our goal in our lab is to build these nanorods and get them all to point mostly toward the sun, but do them from very cheap materials in a way that we can use materials that have never been used before in solar cells because they're simply too impure or they're too defective to collect carriers for the whole depth. But if we make them small, they'll be able to go sideways and we'll get them. This is the periodic table in our laboratory. It's not the normal periodic table. This is a plot on a logarithm scale of the relative abundance of elements in the crust of the Earth versus atomic number, and we have a line that we don't work with anything below the line. We don't work with indium. There's not enough of it. We don't work with ruthenium or iridium. There's not enough of it. We only work with Earth-abundant elements. You can decide whether or not we're crazy by the fact that we're making solar cells out of rust and fool's gold in our laboratory. I think we're pretty crazy, but, you know, that's pretty good. Because, for instance, rust, hematite, is non-stoichiometric. It's well known that you need a few microns to absorb sunlight. It looks like rust. It's well known that the excited carriers can't last more than 30 nanometers. That means most of that 1 micron is just dead. But if we make a nanorod that's 1 micron long and only 30 nanometers in diameter, we can still absorb all the light and move it 30 nanometers sideways and pick them all off. The same thing will occur with fool's gold pyrite or with cheap silicon and so on. Now, there's one other important point, and that is we decorate these things with catalysts that can make fuel from the sun, but we can use cheap catalysts. The reason is that we have a lot more surface area per unit of projected area than we would in a planar crystal. And so we don't need the tremendous activity of platinum because we can load this up with a cheap metal like cobalt or nickel, which is 1,000 times worse than platinum, but we have 1,000 times more of it to do our job, and that's a really good trade. So we're trying to build these rods in pieces. Now, because of time, I'm not going to go into all the technical details of how we do this, but I'm going to show you some pictures. And let me skip this first set right here. So you'll excuse me for this, and I know I have a picture here which takes forever to load, and I'm going to go through it. And I know if I don't wait to go through it. So we started with one material, cadmium selenide telluride. We're going to make these nanometer scale rods. We do this by making a template. This is alumina. It's just aluminum that's oxidized. But we can oxidize it to make these little pores that are a few hundred nanometers in diameter over very large scales and as deep in this top-down view as the thickness of the alumina. And then we can electrodeposit, the same way you plate silverware with metal, this photoactive material inside the pores of this template. We do this in a simple way. We start with our porous alumina. We then sputter a layer on the back just to demonstrate that we need that to prevent the electricity from going the wrong way. And then we put a metal on the back, in this case titanium, from an electrode or sputtering deposited. Then we electrochemically grow our rods. They're insoluble in a basic solution of water, but the alumina dissolves. We dissolve the alumina, we're left with this carpet of rods, all pointing toward the sun. This is a cheap material that's defective enough that if we had the same thickness in a planar structure, we know only the top 1/3 would be photoactive and we couldn't make a good solar cell. But in this nanorod geometry, we should have plenty of short dimensions to get them all excited and collected. We actually infiltrate these pores with a liquid just to demonstrate that we can collect these carriers and make fuel. Here's an example of some of these rods. An electron diffraction data set shows us that they're what we say they are. These are the rods after the alumina template has been dissolved, so we end up with the negative of our template where all the holes are filled. They look like a little Berber carpet from the top-down view. And most importantly, when we actually probe the photo response of these relative to the wavelength of the sun, we see that in fact very deeply penetrating red light, which would not lead to collection in the planar structure, should lead to collection sideways at all wavelengths of light in these nanometer-sized rods that are all pointing toward the sun. And in fact, we see exactly that. When we measure the amount of current that we get as a function of the wavelength of the light, when we've made the planar structure, we don't see much current collected through most of the red and the green and the blue, but when we measure it in the nanorod structure, we get it all. So this demonstrates that we can take a physical object, which on the macro scale would have been rejected for use in solar cells, and make it work just fine by copying what nature does with trees. Well, then we switch to silicon, because we want to make silicon, which is 90% of the solar market, as our cathode to make hydrogen. And I'll run through this relatively quickly, but I spend an hour talking about this part in technical detail to anybody that would listen, and I'm happy to do that later on also. We started with porous alumina. We had a catalyst that allows us to grow this from the vapor phase. That catalyst in this case is gold. But gold is not really allowed in our lab, so now we're up to nickel and copper, and they're allowed. And we put some mounting wax on top, and then we put a substrate on the bottom that's nickel, and then we take the wax off, and then we grow silicon from the vapor phase by a really cheap process practiced on the size of this building to coat glass from the chlorosilane process. This isn't expensive silicon. We don't purify it. and that's heretical. And it's got gold in it, and that's heretical. No one would make a computer chip out of gold-filled silicon because the lifetime of those excited states only moves carriers 1 micron, and we need 300. That means on this scale, only this little bit would be photoactive, and the rest of it would be dead. But these rods are only going to be less than a micron wide, so we should collect them all from all their carriers. We then etch off the alumina and end up with our silicon forest. Here's this forest, beautiful forest of silicon, all pointing toward the sun. You know, we now know we don't need them all pointing toward the sun. They don't have to look like aspen trees. They can look like your lawn and blades of grass. That's what nature figured out. Fill all space and mostly point toward the sun, and we're working on how to do that also. We did an important experiment with these rods. We actually measured their physical properties. And we found that as we scanned the light beam on a micron scale, remember a human hair is about 10 microns, so this is smaller than that, away from where we collected electricity, that we could collect that electricity for distances on the order of 2 or 3 microns. We went to all this trouble to make these rods a few hundred nanometers, tenths of microns. And then we realized that we didn't need to do that. Because if in fact we could collect for 2 or 3 microns, we don't need little thin grasses, we can have big barks on our trees. And so we need to make things on the order of 2 or 3 microns. Now actually this on large scale had never been done before. So we had a challenge. How do we make silicon rods that are microns big? We use that same method, the vapor liquid solid growth method, where we first imprint a silicon wafer with little templated balls of gold, nickel, or copper. In the vapor liquid solid growth method, this catalyst cracks that chlorosilane and makes a rod of silicon grow underneath, and then the ball rides on top. So this is just like biofuels. These are seeds of corn that are growing corn cob stalks straight up from the substrate. And you can get more money if you call this nanobiofuels than if you call it semiconductor rods. So that's what we call it. We actually had to develop a lot of chemistry. These little balls are isolated in an oxide-coated template because otherwise they spread all over the surface and we had no pattern when we were left. But after Harry Atwater's group and my group worked this out, we can maintain the template. When we start with this template, these are 50 micron diameter lengths. These are 2 micron diameter imposed rods. And this is my favorite picture. This is what we get. This is 100 microns. This is a square centimeter of nearly 100% vertically oriented rods that have grown up from this substrate right toward the sun. Here's a side view of that. Here's 30 micron diameter pictures of the rods growing uniformly, little catalyst balls right on top. We can use that later on, and we can grow these. This was half an hour of growth just out of a chemical vapor in an easy scalable method. These are really cheap materials, and they only last in carriers 2 microns, but they're tall enough to absorb all the sunlight, and they're wide just enough to get them all collected. We've made solar cells out of these materials. We've also made fuel from the sun out of these materials. We know right now, actually, for the aficionados, that we have a little bit of gold segregated onto the side walls, and that's got a little bit of recombination current. So these aren't really good solar cells yet, but we know why that is, and we're getting there. Going to etch it off, and our theory says that we should be able to make 15% efficient solar cells from this really cheap process, whereas the best you can do in the most expensive solar cells is 25%, but the hope is that this will really, really lower the cost. There's another really interesting point. Here's nickel or copper, in that if we only grow solar cells off of a wafer of silicon, it's arguable that that doesn't matter much. Because you can't put that on your roof. You have to pay somebody to put this wafer of silicon with wires on your roof instead of just a wafer of silicon. But we can do better than that. Because, in fact, these wires can be peeled in a piece of plastic. This is just fish tank goop. It's polydimethylsiloxane. It's the silicone goop that you use to seal the fish tanks. And it turns out that's viscoelastic, in that its elasticity changes with the speed at which you peel. This is just like a Band-Aid where you pull it slowly not to peel your hair, but if you pull it quickly, all the hair comes with it. And in this case, our hairs come with it too, our silicon hairs. So we just put it on really slowly and we peel it off. And then we end up with these rods in a piece of plastic. And so now we have oriented rods pointing toward the sun that can be rolled up and sent to you like bubble wrap. Okay. Organic solar cells are made out of organic plastics that are unstable in the light but are processable. Inorganic solar cells are made out of crystals that are stable in the light but can't be rolled up because they're brittle. Here's both cases in one. We can do better than that. Not only can we keep the periodicity of the rods, but we can actually add a monomer material in this goop that when it cures, it will evaporate. And so we can make it thin. I promised you early on that we'd have a membrane. And here's a roll-up membrane, and now this plastic is thin and the rods stick up as if they were a hairbrush. There's no loads on anything but the ends of these rods, and so we can completely roll them up and completely unroll them and they don't fracture. In fact, we can bend them back on themselves, and now you can see the piece that we're making of that initial membrane where this points toward the sun and the catalysts are here pointing in water to make hydrogen, and then the oxygen is on the other side of this piece of plastic that's evolved in the other physical space in our membrane. Now, it turns out that this membrane, polydimethylsiloxane, our first generation, doesn't pass protons, and so we have to fix that problem, but we have ideas on how to do that. It also turns out that after we've peeled, what we're left behind is we're left with a shaved piece of silicon. We have little stubs behind. Those stubs, when you put them in an ultrasonic bath, just go away. And that means we're left with holes in our oxide template that we can electroplate new catalyst again, and grow again, and peel again, and grow again, and peel again. So the wafer is a stamp, and then we just have transferred all the growth into oriented rods in a piece of plastic. That's a wonderful thing because we can grow at high temperature, we can do all the process steps we want, which plastics couldn't normally tolerate, and then we can transfer all of that light absorption and device stuff into a piece of plastic that we can roll out and put on your roof. And so we're working, this is the first template, this is the fourth template. We extrapolate, you can do this many hundreds of times off a given wafer, and by that, the cost of the wafer amortized is just negligible. We can also grow polymer in between the wafer. We have chemistry to do all that. And so you can see how we're putting the pieces together. Now, this silicon is one side of this piece. We need the other side. We know what the other side's going to be. That's going to be something that's stable in water, like rust. So if we put together the piece that makes the hydrogen, we need the other piece that makes the oxygen. And we know the answer is going to be just laminate these two pieces together like making a driver's license. We have nanowires made out of rust as advertised. Same idea. We grow them in long enough to absorb the light, but narrow enough to collect all the carriers. You would reject rust as a solar cell material because you couldn't make the rules work in a conventional design, but we can make them work just fine on the nanometer scale. And the idea is that you can grow these rust-embedded polymer independently of growing the other piece. You can optimize both pieces and then bridge them across this membrane to make fuel. Now, we know, just like Melvin Calvin said, that when we put these together, this isn't going to be the end, it will be the beginning. We know that when we put them together, that we'll still probably need better catalysts, we'll still probably need better efficiency, and we'll still probably have to learn how to make them in mass and how to roll them out onto your roofs. But that's why we get paid. So this is our scheme. Let me comment that everything I showed you today, from concept to where we are, was done in the last year and a half. So this is what can happen when you get a lot of very interested people working on really important problems, because, you know, these days my students are working on this like their lives depended on it, which is probably the right way to think about this. So in the end, let me summarize that without massive quantities of clean energy, like it or not, CO2 levels are going to rise. We need to conserve energy. You need to do that in order to hold what is otherwise an impossible problem to a potentially manageable one. You know, our job should be to manage the unavoidable and to avoid the unmanageable. Right? Now, actually, I stole that from my friend Tom Friedman, but he steals my lines all the time, so that's fine. The only supply-side cards we have are clean coal, if it works technically, our nuclear fission, if we dare go there with 10,000 plutonium-containing reactors in our world, or if we find a way to make cheap fuel from the sun in some combination of those three. You know, we absolutely need to conserve energy, but at the same time, no amount of conserving energy ever turned on a light bulb. No amount of conserving energy ever put food on somebody's table. You still have to make massive amounts of clean energy if you want to have population and economic growth and cut emissions within our lifetime. And remember, unfortunately, it doesn't go away. That means that doing this 45 years is 45 more years of emissions under our belts that are going to be there for 3,000 years. I personally don't think we should go there, at least don't feel so good if we do. We have to find a way to store that energy if we're really going to use the sun. Our little piece of that is to use these trees and rods and forests and grasses and try to make them out of really cheap materials in forms that people can roll on or paint on, because I want you to be able to go to Home Depot and buy a bucket and feel good about putting sunlight on your roof and in your fields and on our roads, as opposed to just changing your light bulbs. And I think that's what we need to do to get from where we are now in order to get to this large deployment scale. And we need catalysts to do this. And it's this part, as well as these new geometries that scientists at Helios are working on, that scientists in our group are working on, and now more and more around the world are working on, because we know we really don't have that much time. 2050 isn't 40 years from now, it's kind of 10 years from now, because if we're going to actually make this work, we have to figure out how in time to actually build up an industry and deploy it. And so we've got a ticking clock, but I think we're up to the challenge if we keep at it. So with that, it's been an exciting year and a half, and I hope I've captured for you both the challenge, the policy aspects, and why it's really important that we let scientists go at this problem, and we're trying pretty hard to do it. So with that, thanks so much for having me, and I'd be happy to answer questions. There's one right there.
How do you contact the solar cells you make out of the little rods?
Yeah, the question was, how do we make contact to the solar cells? So the bottom is easy, because that's a conducting polymer, or in some test cases, just plated metal, as I showed you. The top, in the configurations we use to make fuel, is just a conformal liquid. So that's easy. It's water. It doesn't absorb light. We dunk it in water with salt, and that's our electrolyte to make our solid liquid contacts. Now, actually, we have other ways of doing that, where we infiltrate the voids with a conducting polymer, and that makes side contacts. We don't want to contact the tops, because if we contact the tops, that's not our geometry. Our geometry is this tree radial geometry to make sure we collect carriers uniformly along the side dimensions. So we have to contact the sides conformally. We either do that with a liquid or with a conducting polymer. But where that will end up, we don't really know. That's one of the things we really have to work on, how to do really well. But we've got a starting point for that. Let's go back there.
Can you imagine this being completed and in operation? Is this a material that is water pervious, i.e. water could percolate through the nanoforest? And also, is it structural, that is, cars might be able to roll on top of it?
Right. Well, we're not there yet. So we could imagine, depending on at least the interesting thing is by taking these hard materials and blending them with these soft materials, now you can imagine combinations of materials properties that you couldn't have when you were limited to one or the other, right? So we can wildly speculate that it would certainly be possible to take material that was rubbery, almost asphalty as one of the parts, and have little rods pointing up. That's wild speculation now, but it's not beyond the realm of what we know. 2 years ago, if you would have told me we would be making silicon rods in a piece of plastic that we could bend around and roll up, you would have thought I was crazy, but we're doing that now. So we haven't done it, but there's a path potentially to do that. And the interesting thing from our viewpoint is we know there are membranes, like fuel cell membranes, that manage protons. One of those materials is Nafion, for instance. And at some level, this is just the opposite of operation of a fuel cell. In goes fuel, there's a membrane, fuel goes in on each side, and out comes electricity. We're putting in that electrical energy equivalent from the sun, and across that same type of membrane, out comes fuel. The other beautiful thing about this is, if indeed we develop catalysts that can make this fuel, those same catalysts have to undo that process chemically and use the fuel. So the advances that will come about in fuel cells are going to be synergistic with the advances coming out in forming the fuel, because that's a common technology platform in both cases. The difference is that we're generating our energy from absorption of sunlight instead of getting the energy out as electricity from that. So it's the reverse, and that's in part why we work with the fuel cell people to learn what their membranes are and use them. Now we have different constraints, but there's some common ground there. Let's go up here.
It seems like in California we get all these fires every year, and so these trees are going to burn anyway. What are the numbers, I don't know if you know this, but what are the numbers on a fairly dry area like California that does have a lot of trees? If we managed our forests better and burned all these trees with 5,000 local kind of coal-fired power plants, but not coal-fired, but wood-fired, what would the numbers of that be?
Okay. So I think the question is if we actually burnt those trees to make energy instead of just letting them burn to make heat but with a fire, how much energy would we get? And I think disappointingly the answer is maybe in California, where we're having a lot of fires, we might get something reasonable, but globally you don't get very much. The other way to think about this is what happens. You know, people say, well, when you add more CO2, plants are going to grow faster, which of course we know they do. But what really happens is there's an amount of carbon already fixed in all the trees and forests and plants on our planet at steady state, because they grow until on average they die, and so you can add up how much is there at steady state. If you doubled the CO2, they'll grow faster, and so there'll be more there at steady state when the rate of their growth equals the rate of their death. And natural causes contribute to that, and we contribute as deforestation to that too, right? But at steady state, that total increase is worth 5 more years of human anthropogenic fossil fuel emissions. So it's good to plant trees, and it's good to stop deforesting, but it's this cumulative effect that is the real problem, that it's not just stopping the rate of increase, it's actually stopping the rate, period, that makes life so hard. To give you a feeling of how hard this is, with all the talk about Kyoto, you know, in the 1990s, we were increasing CO2 emissions globally at a rate of 1.1% per year over that decade. And then we talked about Kyoto, and you know, we collectively, our planet, tightened our belts and showed the world what we could do. And you know what we did between 2000 and 2006? We tripled it. And now the rate of increase is 3.1% a year. And in fact, carbon emissions have risen at a more rapid rate than the most pessimistic of all the predictions as late as 1992 were. So turning that over and going down will be a significant change and disruption in probably the biggest business in the world, the business of where we get all our energy. And you should not underestimate the challenges involved there. And we've got to think about doing that.
Excuse me if I misunderstand. Is your distribution medium not electricity, but fuel cells? Does the smart grid become unnecessary?
There's nothing bad about a smart grid, but there is no technically credible way to store massive quantities of electricity. Smart grid or unsmart grid, you know, if you make it all during the daytime, where are you going to put it all to use it at night? If you made it in the summer, where would you put it to use it in the winter? If you made it on a sunny day, where would you put it on the next day if it was a cloudy day? We don't do any of that right now. right? The grid is just a bunch of wires putting in energy from somewhere and putting it out at the same time somewhere else. That's a little bit of short storage. In fact, the only cheap way of storing massive quantities of electricity is pumping water uphill. Is pumped hydro right now. And that's good for summer, winter, because you can fill up a reservoir slowly in the winter and empty it slowly in the summer. But there's no good way to store massive quantities of electricity from day to night. And so no matter how smart your grid is, unless you can envision tremendous resources of water going up and down every day or batteries, think about how long you can run your house on your car battery. Not very long. So you need tremendous banks of batteries to store all this energy. Whether or not you get it from wind, whether or not you get it from sun, energy storage is a key necessary technology to enable large amounts of renewables for both electricity and, more importantly, for energy. Without energy storage, you just have the ability to use those intermittent sources when nature decides to give them to you. You can't build an energy system around that.
Excuse me, could you elaborate on that a little bit in your system? In other words, apparently you are creating hydrogen fuel. How would you store this efficiently?
Well, there are several ways to store this efficiently, as I said early on. We are only working on making hydrogen fuel from water because that's the simplest fuel-forming chemical step. And so that's where we're starting with this. But we also know that there are catalysts that can take carbon dioxide with hydrogen and make methanol or ethanol or other fuels. So the key isn't that we're making hydrogen. The key is that we're making a fuel that can be converted into a other fuel. If you wanted to think about this, you could think about bubble wrap and water coming in and hydrogen coming out the other side, or maybe it's liquid fuel coming out the other side. Let me also say that the last place that you would use hydrogen in an energy economy is in transportation. Because there are only 4 things you have to do that. You have to be able to make it, you have to be able to distribute it, you have to be able to store it on board a vehicle, and you have to be able to efficiently use it. And the only problem is we don't know how to do any of those 4 right now. On the other hand, if you could efficiently make hydrogen cleanly, cheaply, there are lots of uses of it, just like we use natural gas, for home heating, for industrial uses, when mobility and storage and energy density are not significant constraints. And so you can easily see how you would use a fuel to buffer the intermittency of renewables in many applications without having to solve the technical challenges first of using it in transportation. And if we don't solve it in transportation, there are many other transportation options of what a fuel is. Maybe it's electricity and batteries, maybe it's biofuels, maybe it's some combination of all of this, but you don't have to depend on hydrogen as a fuel for a car to be able to use renewable fuel in our energy system. And that's the last place you do it because it's so demanding when there are lots of other easy pickings first. There was a person. What happens to the oxygen? We put that in the air, which is already filled with oxygen. And that's why you must make oxygen. If you're going to make a fuel, you can have a choice on what you're making on the other side. You can make water into hydrogen. You can use that hydrogen with carbon dioxide to make a reduced hydrocarbon like methanol or ethanol or butanol. You can make any of those reduced things and call it a fuel, provided you make oxygen on the other side. Because you let the oxygen go, you carry the fuel with you, and you grab back the oxygen from the air somewhere else. If you don't make oxygen, you haven't made a fuel, you've made a battery, because you have to carry both things with you. Right? Yes.
Where are you going to get all this water from?
Then no problem. Because first of all, you don't need very much water. Second of all, it can be salt water. Thirdly, it's completely recycled because it goes into the air, it burns as hydrogen and oxygen, which makes water, which comes back again. And if you calculate the amount of water compared to the amount of drinking water that we use, it's not very much, and it's only used once in the whole cycle because it's conserved. So it's not a disposable quantity.
I have a comment that in California it is about the water, and it turns out that the 4 horsemen of the apocalypse, nuclear, coal, oil, and natural gas, use 136 billion gallons of water daily in the production of electricity. Only agriculture uses more water daily in America. And solar electric roof shingles and solar panels use no water in the production of clean, renewable electricity. So it's important that if California wants to preserve its freshwater resources, that we move to a solar electric infrastructure. Thank you.
Good. So I don't disagree that it's really good, and we should be doing much more if we can and think we can afford it. By the way, the cheapest way to make electricity from the sun is not to put solar cells on your roof. The cheapest way is to have PG&E and the utilities do it at utility scale with solar troughs and solar thermal. That's 10 cents a kilowatt hour, or 12, and it costs 25 cents a kilowatt hour to put it on your roof right now. Now, the reason we do that is because they're different markets. Because in utility scale, at 12 cents a kilowatt hour, that still costs disfavored compared to generating it from hydro or from coal at about a nickel a kilowatt hour. So it costs the utility more. If it's on your roof at 25 cents a kilowatt hour, you pay more than that in peak from PG&E because you're paying for the grid and the taxes and everything else. So it looks better when you're competing at retail with photovoltaics, even at more expensive cost to the end user, than it does at utility scale at 10 or 12 cents a kilowatt hour. The other thing you have to be careful about is that you can't go to more than 10 or 20% intermittency without storage, which we have no technical solution for yet. And the other thing you have to be careful about, and I'm involved as an advocate for using renewables, but I'm really involved as an advocate for thinking about not rolling the dice with CO2. Like it or not, the facts are right now solar cells pay themselves back, silicon, at 3.8 years, 4 years roughly. Crystalline cells, 4 years of the energy they produce is needed to make them in the first place, in a kind of optimistic scenario. That sounds great because they last for 30 years. On the other hand, it's very easy to show that if you're growing at 30% a year, that you need all the energy from all the cells just to make the next year's worth of cells. And you need that for the next 30 years of growth. So we can feel really good about putting solar cells up, but with our current crystalline silicon technology, we're not going to displace an ounce of carbon dioxide in our lifetimes with the current technology. That's why we need to do everything we can do to lower the cost and the embedded energy and do more than just deploying what we know how to do now. We've got to be investing in R&D to get cheaper, better, next generation products in energy.
How close are we, like time-wise, to creating an industrial size level?
How close are we to having, okay, so the good news here, energy in the United States alone is a $3 trillion a year industry. Globally, ExxonMobil is only 5% of the oil market. So there's 20 ExxonMobils just in oil, and oil is only a quarter of total energy consumption. There are kind of 100 ExxonMobil-sized companies to be had, waiting. How close are we to making 5 ExxonMobils? Well, you know, I think if ExxonMobil thought we were really very close, they would have gobbled us alive right now. They're funding some of our research, but not yet. How do we accelerate that? Well, how do you tell a chicken to lay eggs, right? And the answer is, if you're not getting enough eggs, the only proven way is to buy more chickens, right? This is why you have to have people like Helios and people like us and people like you really working on this problem. The way I say it is pretty simple. Just if we don't build the next nano widget, if we don't build the next 5 generations of Wi-Fi, the world's going to stay the same. It may not be better, but it's going to stay the same. If we don't cure cancer, and I know personally from my dad, it's not fun, but if we don't cure cancer, the world's going to stay the same. But like it or not, if we don't fix this problem in the next 20 years, because it lasts for 3,000, then we can say that if we don't fix this problem, that the world is never going to be the same. That's why we've got to work on it. Yeah.
You mentioned that one of the problems for the plan a structured solar cell with the charge carrier cannot travel to the surfaces. So can you comment on the possibility of using the pyrite, which is also earth-abundant material, and using that as a photo
Yeah.
absorption method?
So the question is, can I comment on using pyrite? We have proposed to use pyrite. We haven't done it yet. It's been used in the literature in the planar structures with the predicted inefficiencies that you would have from a short diffusion length material like iron disulfide. But we think we have a route out of that. Now, if you're an aficionado, you know one more thing. You know that when you go to these high aspect ratio structures, you transfer the problem from making pure bulk. Now you relax that, can have impure bulk, but now you have a lot of surface atoms, and those surface defects can eat you alive unless you passivate them. It turns out on silicon we know how to passivate those surface sites. We can methyl terminate those rods instead of hydrogen terminate, and that's why they work at all. So we have a way to really lower the surface recombination velocity of silicon, and we knew that going in as chemists. We don't yet know how to do that with pyrite, but have some ideas on how you would take those iron or sulfur atoms at the surfaces and tie them up and fool them into thinking that they were bulk also. So this isn't just slap it together. You know, we know there are certain boundaries that we have to break through, but it's credible that we could if we try. We're done, or what? See, I've got somebody back here saying, okay, I've got one more and then we'll stop. And I'm happy to answer questions after this, yeah. Yeah.
In what relationship is just the ratio of the height to length of this thing? In other words, is orientation of these trees important?
Yeah.
Are there different orientations?
Right. So, in fact, we probably want it like grass instead of like aspen trees, right, where it fills all space. Now, there are interesting properties of if you get the rods dense enough that they can bounce light around and have photonic band gaps and other light absorbing and trapping properties. The key design rule constraint is that the diameter of these rods should be twice the diffusion length so they can be efficiently collected. So that's what the theory tells us to do and what we do. But the exact, whether or not it's carpet or grass or trees would be great, right, with branches and Fibonacci series that are optimal light absorption. Nature figured out how to grow a tree to optimally absorb sunlight and without shading of each of the individual branches. We've got drawings on the board of how you would catalytically branch and instead of growing rods, actually grow forests that look like trees. There are lots of things to do there. Those are fun things to do, actually, that people are working on, including us. With that, I think we have to stop this. I'll be happy to hang around and answer some more questions as high at technical levels you want to go or policy-wise. Thanks so much for having me, and I'm happy to do this. Okay.
We would like to thank Dr. Nate Lewis for a fabulous talk tonight. Before ending tonight, we would also like to thank our co-sponsors. This is the last talk for the series, for the 2008 Spring Series Lecture Series, and we would like to thank everyone for supporting us this spring. We would also like to give a special thank you to Terry Powell. I know I've seen her. She was a great support in setting up these talks before retiring from Berkeley Lab. So we'd like to say thank you. We'd like to say good night to everyone.